Okay, so in these 3 lectures, I'm going to discuss the wave equation in dimension 3+1, and I'm going to use the following 2 references. The first is a book by Saki, that's the lecture on nonlinear wave equation, and another is the lecture note of Formosa and Ronowski about linear wave equations in black hole spacetimes. And the purpose of these lectures is to introduce a powerful tool in studying the wave equation, which is so-called vector field method. To illustrate how to use that, we are going to discuss 3 topics. Today, we are going to prove the basic local existence and uniqueness for the wave equation of the solution. And then we are going to discuss the long-time behavior of the solution in the Minkowski and probably in the Schwarzschild spacetime. And at the end, we are going to discuss a semi-linear wave equation still using the vector field method. Okay, so that's the plan for the lectures, and let's get started. Well, first, I need to tell you what is a wave equation. The most standard wave equation is the following one. Box u equals minus d squared u dt squared plus the Laplacian in the rest directions. We have x, y, and z. Okay, so this is the most standard wave equation. And here we can see that the t variable plays a different role from x, y, and z. So this is the time variable. And the other 3, they are space variables. So we use different notation to distinguish them. In these lectures, I'm going to adopt the following notation, xa, xb, that will be indicating, well, this coordinate system, and xi, xj will be used to denote x, y, and z. So this equation, sometimes we just write it as d squared u dt squared plus summation. Okay, so this is the standard wave equation. And in general, as long as we have a Lorentzian metric, may be Lorentzian, then we can form the corresponding wave operator. That is G upper AB, gradient A, gradient B of U. So the trace of the Hessian. For example, the above standard wave equation corresponds to so-called Minkowski metric. X squared plus dy squared plus dz squared. This is called Minkowski metric. Therefore, we use this, the corresponding spacetime is called Minkowski spacetime. So here we can see, well, that's not pretty similar to the Laplacian Beltrami operator. The only difference is we are contracting the Hessian using a Lorentzian metric, which has signature minus, plus, plus, plus. And just like the Laplacian equation, you can view wave equation as Euler-Lagrange as the critical point of a function. So box GU equals 0 is equivalent to say that U is a critical point. of the Dirichlet functional, which is the integral, or more or less the gradient squared of u. But remember, now the metric is Lorentzian, so this integrand may not be positive. But in any case, we can still write down this functional. And wave equation corresponds to a critical point. In other words, that is the Euler-Lagrange equation. And because of that, it has a corresponding stress energy tensor. dAu dBu minus a half GCD This is called stress energy tensor. This could be derived if we take this functional E and then take the derivative with respect to the metric. The result will be this symmetric two-tensor cube. But, well, in any case, for any solution, for any function u, we can form this symmetric two-tensor. And this is the core of the vector field method. Vector field method simply means take this symmetric two-tensor, contract it with certain vector fields, then apply divergence theory. That is the vector field method. It sounds simple, but that's actually pretty powerful. Okay, so for this stress energy tensor, it has two very important properties. First, if you contract it with two future vectors, it will give you something non-negative. That is more or less du squared when x and y are future vectors. So it satisfies the energy condition. Second, it is divergence free. Once we take the divergence of Q, we see the box hits U times gradient U, provided box U equals 0, this will give us, well, 0. This one leads to so-called the conservation law. Suppose K is a Killing vector with respect to this Lorentzian metric G. Then we times Q by K. We get a one form, and the divergence of this one form equals 0. Because, well, Q is divergence free, and if the derivative hits K, K is Killing, we get an anti-symmetric tensor, and Q is symmetric, their contraction will be 0. Once we have something is divergence free, that leads to conserved quantities. And let me give you the following example. That is will be called the conservation of energy. Sorry about that. Okay, so let's say we have a standard wave equation in the Minkowski space-time. So we form the stress energy tensor QAB, just like the M side. And now let's choose the Killing vector to be the time translation, T. we know the divergence of Q times T equals 0. So let's apply the divergence theorem in the following region. Here, this vertical is the t-axis, fixed to numbers T2 larger than T1. The thin bounding in between, I will denote it by omega. Both of these horizontal lines, they represent R3. So it's a picture in 4D. Okay, so let's apply divergence theorem. The bulk is QAB TB. Of course, it is 0. The integrand is 0. And the bulk equals the boundary term. That is integration. On the slice, t equals T1 QAB TB times NA minus t equals T2 QAB TB times A. Here, the N is the unit normal vector of these two time slices. In this case, well, actually, it coincides with the vector ddt. Okay, now the energy condition, the positivity come into play. The integrand QAB TB NA is non-negative, and more precisely, it is of the following form: a half dtu squared plus summation I from 1 to 3 diu squared. So it's not only non-negative, it captures the H1 norm of U. Then let's define the energy. Et defined to be along the time slice. T1 equals T1 half dtu squared plus 1 to 3 . To summarize what we have done, we have proved that this E is a conserved quantity. Et1 equals Et2. So, which is called the conservation of energy. This is probably the simplest application of the vector field method. We time the stress energy Q by a vector, then apply divergence theorem to see what will we get. Okay, now let's talk about the existence and the uniqueness of the solution. And let's consider this class of wave operators, P. The coefficient between before dt squared is phrased to be -1. The spatial direction, we have a Riemannian metric. So those two are the leading coefficient for the second order derivative. And there are some other lower order terms. And we put the assumption that the Riemannian metric is uniformly elliptic. Furthermore, everything is smooth with bounded CK norm. So we consider this type of wave operators. And we want to study so-called the Cauchy initial value problem. That is the following system, PU equals a function, capital F. And we want to assign its initial value and the initial velocity. P0x is a function, fx, dt, x is gx. Here I'm using x to stand for the space variables x, y, and z. So this system is the Cauchy initial value problem. And these three functions, capital F, small f, and g, they play different roles. We are going to call capital F to be the source. And the other two, we are going to call them initial data. Now, let me tell you, let me give you the definition of the weak solution to this Cauchy problem. U is a weak solution star in 0t to plus R3 if, well, it times a test function has the correct integral equality. For any test function phi, which is smooth with compact support, it holds that the integral from 0 to capital T, phi times f equals integral 0 to capital T, p star phi times u plus some boundary term. On t equals 0. So here, the p star is the adjoint operator of p. So this is more or less standard one define the weak solution through integration by parts. Move the derivative to the other side. That's why we see the adjoint operator, p star. And in doing so, we are going to pick up the boundary term at t equals 0, which will involve the initial data, f and g. Their explicit form is not that important, so I will just leave it there. And I want to emphasize that these test functions is assumed to be identically 0 near capital T. So we do not pick up the boundary term there, but we do pick up the boundary term at T equals 0. Okay, now we can state the existence and uniqueness theorem, which is the focus of today's this lecture. So let's fix a time and an integer. Suppose the data, the initial data f and g, and the source capital F satisfy the following regularity assumption. For f, we assume it to be hs plus 1. For g, we assume it to be hs. For f, we assume it to be L1 from 0 to capital T, which maps to hs R3. Okay, so that is the assumption. Then star has unique solution. U, which lies in C0, 0 to capital T, maps to hs plus 1, And if we can take one time derivative, C1, 0 to T, HS, R3. Okay, so this is the existence and the uniqueness theorem. Then let's give it a proof. On the left is what I wrote on the previous page, the Cauchy initial value problem, and the theorem number 1. So the proof has several steps. In the first step, we assume, well, the data are all smooth. Assume F, G, and capital F, they are all smooth, and they all have compact supports. Well, in this case, we can actually assume F and G are 0. Simply by substitution. So the only thing left is the source term, capital F. And the goal is to prove that we have a smooth solution. Cool. By the way, at the beginning, I'm going to focus on the existence part. So the proof, everything here will be about existence. Okay. So, well, the weak solution is defined by the integral equality. So let's write down the corresponding functional. Define LF. And first define the linear space. B is defined to be the image of P star acting on the test functions. T cross R3. F is a functional defined on V, which is LF P star V is integral V times F. And this space V, well, it is a smooth operator. It is a differential operator with smooth coefficients acting on smooth functions. So it is still, there are still smooth functions. In particular, that would be a subspace of L1, 0 to T, H minus S minus 1, R3. Here, I should first fix an integer. It holds for any S, simply because everything is smooth with compact support. And we claim LF is a bounded linear functional. It is bounded with respect to this norm. Suppose this claim is true, then by Hahn-Banach theorem, we can extend it to the whole space. Which is still a bounded linear functional. From Reid's representation, this one will be represented by a function in the dual space. The dual space of L1 is L infinity. The dual space of H minus S minus 1 is in H S plus 1. such that LF P star phi is simply U times phi. And this is defined to be the integral of phi times F. So U times P star phi. In other words, U is a weak solution. And up to now, what we know is, well, U is in L infinity from 0 to capital T to HS plus 1. But here, the integer s is arbitrary. Therefore, we can increase s as large as we can. U will be in L infinity. H infinity. In other words, it is smooth in the space variables. And now what we need to do is to show it is also smooth in the t variable. And here we are going to use the equation. dt squared u equals minus pu plus gij di dju plus some lower the terms. Basically, the 2 times derivative of u is pu, which is f, plus the spatial applosion. Therefore, that would be smooth. Using that, u will be a smooth function. Okay, of course, by looking at this argument, I implicitly assume that for different s, for different s, we will have the same u. To get that, we actually need uniqueness. So let me make clear here. I assume uniqueness. Okay, so this is the first step. We assumed uniqueness, and we assumed that this LF is a bounded linear functional. Then we get a smooth solution, U. This is the first step. And the step 2 is quite standard. For a general solution, general integral data, general, then we use approximation. The only thing we need to make sure is, well, once we approximate this data by smooth functions with compact support, we get a bunch of solutions. These solutions will be convergent. They will converge to a limiting guy, and that guy will be the solution. So make sure convergence. Okay, so this is the structure of the proof. Up to 3 things. We need to assume uniqueness. We claim LF is bounded, and we need to make sure the approximation will give us a convergent sequence. All of these 3 can be resolved by a priori energy estimate. Okay, so here is the assumption of boundedness of LF. Also need to prove uniqueness and the convergence of approximation. And to do that, we need the following a priori energy estimate. It looks a little bit complicated, but let's take a look term by term. It says that for any S in Z, we want to bound some norm of U. Which norm? The term here is HS plus 1 norm of U. Here we have HS, but in the inside we have U with 1 derivative. Alpha is a multi-index less or equal to 1. And we want to bound this guy at time t. And what we can use is here, this should be at t equals 0. The thing in the blue box is the initial data. That involve the same norm of U, but at time 0. And the next term is the contribution of the source. That's something depending on PU, and it is its HS norm. Okay, so this is what this a priori energy estimate says. To put it simply, once we know PU is in HS, we are going to know that U is in HS plus 1, provided the initial data is good enough. Here, I would like to compare this with the elliptic operator, especially Laplacian. Suppose we know Laplacian U is C1, then U will be C3. That's elliptic regularity. And here, because our operator P is not elliptic, it's a wave operator. So we only get one order of derivative. And with this energy estimate, the uniqueness becomes pretty simple. Let me just say in words, suppose you have two solutions, U1 and U2. You look at their difference. They satisfy the wave equation with no source and no initial data. Through this energy estimate, it says, well, this guy must be 0. Therefore, those two solutions will be identical. That gives you uniqueness. Also, it will give you the convergence of the approximation. Once you approximate the data through smooth functions with compressor port, this estimate essentially tells you, well, those sequence of solutions will be a Cauchy sequence in the super norm. Therefore, that will converge. And the only thing left is to prove this boundedness, this claim of boundedness of LF. And it goes like the following. LF of P star phi is obviously bounded by the integration 0 to capital T, the H minus S norm of phi times H S norm of F T. And because well F is smooth, it will be bounded by the H minus norm minus S norm of phi. Now what we want to do is we want to use P star phi to bound it. And this is exactly what the a priori energy estimate tells us. By theorem 2, we apply theorem 2 to P star and phi. We get the H minus S norm of phi at time t is bounded by P star phi, it's H minus S minus 1 norm. And we integrate from 0 to capital T. Here we also don't have the initial data because, well, we reverse the time direction and we treat capital T as our initial time. This function phi is assumed to be vanishing at that moment. Therefore, there will be no initial data. Okay. So this is what we get from theorem 2. Use that. We continue the argument is bounded by C times 0 to T P star phi H minus S minus 1 dt. And this finishes the proof of the existence as well as uniqueness of the solution. To summarize, well, to prove the existence, one construct the corresponding functional, which is LF over there. The energy estimate is used to argue, well, this functional is bounded in the suitable space. Then use Reed's representation, we are going to find a weak solution. Later, we upgrade the regularity. And finally, use approximation to get the solution for general initial data. That is the structure of this proof. Okay, so the thing remains, we still need to do is to prove this a priori energy estimate. Which is on the left-hand side. And the argument will go like the following. In step 1, we're going to prove the case for S equals 0. In step 2, we're going to deal with the case S greater or equal to 1, but it can actually be reduced to the case S equals 0 because we can consider V as the derivative of U. Say V equals du dt, du dx, and so on. Then apply the estimate for S equals 0. Using this trick, you can get any integer, positive integer S. And for S being a negative integer, there's a similar trick. Consider V, which is identity minus Laplacian to the power minus S acting on U. So for this V, it has the property that V its H absolute value of S norm is comparable to the HS norm of U. So that's similar to the trick in step 2, just a bit more complicated. Using that, you can extend it to every negative integer. So really, the most important case is when s equals 0, which is the part I'm going to give you a more detailed argument. So let's first rewrite this estimate for s equals 0. For s equals 0, we can rewrite the bound in the following form: e bar a half t is bounded by c times e bar a half 0 plus 0 to t. Pu is L2 norm. Here, e bar t is more or less the energy we discussed before. We integrate along a time slice, dtu squared I u squared plus u squared. The only difference is, well, we have this base L2 term, except that that's the same as the energy. Let me recall it quickly. Okay, so besides this base L2 norm, they are actually the same. So we want to prove this estimate. And let's do it on the next page. And before start to prove it, I would like to compare it with the conservation of energy. If we are, this is the standard wave operator, and we have box U equals 0, by the conservation of energy, ET will be the same as E0. And the difference is, first, we are dealing with more general operator, the wave operator P. And we don't assume Pu is 0. Pu is the source term, and we want to use it in the estimate. But the proof is actually pretty similar. We still want to use the vector field method. We times the stress energy tensor Q with a vector, then apply the divergence theorem. Okay, now let's begin the proof. First, well, let's write down a Lorentzian metric corresponds to this operator P. We call that Pu is minus dt squared u plus ij di dju plus lower order terms. So let's define AB to be the following form. It is -1 in the TD direction. And for the space directions, that would be simply Gij. Then the corresponding box operator coincides with P to the top order, plus lower order terms. Well, let me be a bit more precise. That would be of the form b bar 0 u plus b bar I iu plus c bar u. Anyway, something involves 0 or first order derivative of u. And we write down the stress energy tensor corresponds to this Lorentzian metric G. CD and T is still the vector ddt. So let's apply the divergence theorem in the following region. T slice and the initial slice. Okay. And let's first compute the bulk. Now the divergence of QAB times T, it will no longer be 0 for two reasons. First, this is the box of U is not 0. Second, for this Lorentzian metric G, T may not be a Killing vector. So we can pick up this second term. But all of this can be expressed in terms in this form as Pu, more or less box U, times the first order derivative of U. U. And the second term, well, that will be quadratic in the first order derivative of U, du times du. Therefore, turns AB TB. If we put the absolute value, that'll be bounded by 0 to T operation on R3, du squared plus du times Pu dx dt up to some constant C. So this is the bulk. Along the boundary, well, the integrand is still QAB, TB, NA. N is the unit normal vector of these time slices. But now the metric is not Minkowski, so the normal may not be ddt. But because we have the elliptic assumption, this integrand is still comparable to this du squared. So put them together, the divergence theorem tells us the energy at later time is bounded by a constant times the initial energy plus 0 to T R3 du squared plus du Pu dx dt. Okay, now we need to deal with the fact that in E bar, we need a zeroth order term. We need the base L2 mode. But that's simple. UTX is U0x plus 0 to T dtu dtu dt. Well, just fundamental theorem of calculus. Take the square and integrate it. X squared dx is bounded by a constant 3 u0x squared dx plus 0 to t r3 dt u squared. Okay. And I want to emphasize that the constant here may depend on capital T. So the larger the capital is, the larger this constant C should be. And we add these two bounds. What it will give us is bar T is bounded by a constant times the initial E bar plus 0 to T, E bar T prime plus E bar to the power of half, Pu, it's L2 norm, T prime dt. So more or less du squared together with u squared give us E bar. And from this, one can use the ground wall inequality, the ground wall estimate. You can use ground wall to get to the double star. And this finishes the argument. So to summarize what we did in this lecture, we introduced the wave equation as well as the core in the vector field method, the stress energy tensor. And we use that to prove the conservation of energy and this a priori energy estimate. And using that, we can prove the existence and the uniqueness to the linear wave equation. And in the next lecture, we are going to continue to still using the vector field method to study the long-time behavior of these solutions. Okay, so this is this lecture.